Good morning, everyone. This is the first lecture of Triple 3, and we will review your electrical quantities, Kirchhoff's voltage law, and Kirchhoff's current law. This should be covered in your Physics 72 when you took it. I don't know, maybe the past semester, but I don't know. But without further ado, let's start. The objective of this lecture is to reintroduce to you the quantities that are used in electrical engineering, which are the following, as you see on the screen, and reintroduce also Kirchhoff's current and Kirchhoff's voltage laws. And these are important tools to use for your circuit analysis. So, electrical charges are basically a fundamental quantity of matter. It's a property of matter that causes it to attract or repel or experience a force due to what we call an electric field. So if there's an electric field and the particle has a charge, then the charge experiences some force. So the electrical force can be repulsion or attraction depending on the sign of the charge. We have the positive charge and the negative charge. Positive and negative charges attract each other, while same sign, positive to positive or negative to negative, repel each other. The unit of charge is in coulomb. So these are the interaction. If you have a charge right here, you create an electric field that is flowing radially outward. If it's a positive charge, we call this an electric field source. If you have a negative charge, the electric field goes inside the negative charge, and we call this a hole or a sink. So the electric field can be computed with this. It has a direction. It should have a direction right here. And the force can be computed using this equation. So if you have a positive charge, it repels the positive uh, charge and attracts the negative charge. As you can see, the positive charge or the force of the positive charge moves along the electric field. So once the charges move, create current. And in the presence of an electric field, the charges are forced to move in a natural way. It creates somewhat a electric potential difference or difference in electric potential energy. So what does that mean? A charge at rest will continue accelerating and accumulate kinetic energy. So that means if you look at the positive to the positive, as the positive charge moves away from the source of the electric field, then its potential energy decreases. What happens? It becomes kinetic energy. So let's look at the current. It's the movement of charges. We call the conventional current is used in analysis is we assume it's the flow of positive charges. But in reality, there are no protons, the carriers of positive charge, that can flow freely in a metal. Why is that? Because proton is embedded in the nucleus. In reality, it's actually the electrons that are moving, and they are negative charges conventionally. So the conventional current flows differently from the electron current. So that's the definition of current. Basic definition. It's just the movement of charges. So the rate at which the net charges move past a given area. So it's defined by your magnitude and direction. So it's a vector. So that means if it's a vector, it can have a negative value. That doesn't mean that you have some negative current moving. It's just that you uh, assigned a wrong direction to the current. That's why it's negative. So its unit is in ampere, which is 1 coulomb per second, or uh, the charges passing through an area per second. So if you look at this illustration right here, you have a cross-sectional area. There's a current going in, two currents going in, and since there are no other way the current can go, then this is implied that current I1 is equal to the negative of the current I2. So they flow in different directions, therefore there's your negative sign. So Kirchhoff's current law means that the states that the algebraic sum of the currents at a node must equal 0. So that means if you have different currents converging to a point, depending on their direction, their algebraic sum is equal to 0. So let's assume then that the currents going in the node is positive and the current going out of the node is negative. So the summation of all currents in this node is 0. Therefore, you get I1 plus I2 plus I3 plus negative I4 equals 0. Why is I4 negative? Because the current is going out of the node. So we just set that the current going in is positive and the current going out is negative. But we can set it on a different way. We can assume that the current going in the node is negative and the current going out is positive. And you still get the same valid equation right here. So it's always the convention was where students actually set up the equations incorrectly. You have to mind the conventions used. So if you assume that the current going in is positive, you have to assume that the current going out is negative. So this will make your equations consistent. Okay, moving on. We look at the voltage. We have the current, now the voltage. The voltage or potential difference is a difference basically in potential of 2 points. So you can liken this to your gravity actually. As you increase the height of the object, you get greater potential energy. In this case, instead of using what we call a gravitational field, we'll use instead an electric field. So as you move away from the negative charge, this is incorrect actually. These should be positive. Let me just write it. There you go. These are positive charges. Oops. There you go. So as the positive charge moves away from the negative charge and goes nearer the positive charge, the electric potential increases. Right? So why is that? Think of potential energy as going against the natural flow. If you are in a state of if you're in a state of um, stronger, if you let me rephrase that. If you are going against the natural flow of things, in this example, you're going away from the gravity field, the natural flow is that you're going down. You're going down from a higher elevation to a lower elevation. The natural flow is that if you go higher, you get more potential. Same is true with positive and negative charges. As your positive charge goes away from a negative charge, it has greater potential energy. Why is that? Because positive charges attract negative charges. So, if you move away, if you try to force the positive charge to move away from the negative charge, it creates more potential for the positive charge. And also, as you can see, the positive charge actually moves nearer to the positive charge here at the railings. So as you know, the positive charges repel each other, and if you force the positive charge to move closer to the positive charge, you create more potential energy. So that's the only difference actually of your EPE to your GPE. Your GPE always attracts the body, but it does not have some positive attraction, or sorry, positive repelling force in here at the height, at the higher level of your gravity. So that's the only difference between your electric potential energy to your gravitational potential energy. Right. So that's what I said earlier. To move a particle against its natural path, you need to exert effort. Therefore, you increase the potential of that particle. So, and to move a particle along its natural path, you kind of, quote unquote, recover energy. Therefore, you're receiving work or the particle is expending work. So, it's sacrificing its potential energy. You can think of it that way. So, the voltage then is just the potential difference between 2 points exposed in an electric field. So the notation is this. Double subscript means you're getting the potential difference. So that's VAB, that is the potential at VA minus the potential at B. So if you reverse the notation, you just get the negative sign. So don't worry, if you get a negative voltage, that's fine. It just means that the sign here is flipped. So if you have a negative voltage and this is your convention, plus then minus, it just means the minus should be here and the plus should be here. So it becomes positive. So that's for the double subscript notation. The single subscript notation defines voltage with respect to what we call a reference point. Okay? So with that, we can translate the double subscript to a single subscript through these equations right here. Okay. So the voltage is just the difference in potential between 2 points. In a physical system, it's measured across 2 points called nodes. And there is a difference in charge concentration in node A and node B, giving rise to what we call potential difference. So B here is assigned as the reference point of this device right here. So you always measure the voltage between two nodes. So what is Kirchhoff's voltage law then? Kirchhoff's voltage law says that the algebraic sum of voltages around a loop must be equal to zero. So the summation of voltages here, when you go around from A to B to C to back to A, you get the sum of voltages equals zero. Alright, so how do you quantify that? By convention, if you move from the negative to the positive, you get a positive voltage. If you move from your positive to negative, you get negative voltage. Positive to negative, negative voltage. So let's try to move around from C to A to B back to C. So if you start from C, you start with the negative, going to the positive, so it's a positive voltage. Going from the positive to negative, negative voltage, positive to negative, negative voltage equal to zero. So again, this sign is just a convention. You can set that negative to positive to be a negative voltage and the positive down to negative as a positive voltage. But in practice, you can assume if you're going from negative to positive to be a positive voltage, and it's more intuitive that way, and you'll see later. So let's compare where did Kirchhoff's voltage law come from? So let's compare it in a mechanical system. So assume then that you have a mass m that is moved around 4 points. So at first, the mass is at a height h1 and it's moved upwards to a height h2. So the energy needed to do that is this. So the energy gain of your mass is equal to mg times h2 minus h1, its final state minus its initial state. And you move this mass from this point to this point at the same height but a different x uh, coordinate. So if you move it from here to here, there's no energy that was expended. Therefore, you have an energy increase or decrease of 0 for that mass. That's kind of like an electron moving along a wire. Because if you move an electron along a wire, there's no energy increase because that wire has the same potential all throughout. So think of this movement from here to here as like moving as an electron moving along a wire. There's no change in potential, therefore there is no change in energy. So you move it from here to here, there's no change in energy, therefore it's 0. Then you move the mass from here to here, it decreased in energy. So this is the final state minus the initial state. Then you move it back from here to here. Again, there's a 0 increase or decrease in energy, and it's like moving along a wire. So your mass traveled around a loop. So the summation of energy from here to here to here to here should be equal to 0. Why is that? It's the law of the conservation of mechanical energy, right? So if you move from here to here to here to here to here, the net energy or the net work is equal to 0. If you move around a closed path, the net work is 0. Recall from your Physics 71. So the summation of all energy should be equal to 0. And yeah, if you try to solve, this would cancel with this since it's the negative of each other. So the summation of energy is equal to 0. So example, given Vxy equals 20 volts, Vxz equals 10 volts, and Vz is equal to negative 5 volts, find the absolute value of Vx and Vy. So let's try to solve that. Right. All right. Okay, so Vxy is equal to 20 volts. And that is equal to Vx minus Vy. Right here, also Vxz is equal to 10 volts. And that is equal to Vx minus Vz. And Vz is equal to negative 5. Therefore, it becomes Vx plus 5. So Vz is equal to negative 5. And we can now solve for Vx from this equation. So Vx is equal to Vxz plus Vz, which becomes Vx equals 10 minus 5. You get 5 volts, positive 5 volts. There you go. And finally, you can now solve for Vy, where Vxy equals Vx minus Vy from above. That becomes Vy transpose equals Vx minus Vxy. Okay. So we have now the equation right here. Just substitute the values. Vy is equal to positive 5 volts minus 20 volts equals negative 15 volts. And this is your answers. So, and this one right here. There you go. And finally, for the next, find VB in terms of VC if VAB is equal to VC and VA is equal to 20 volts. So let's list the given again. So right here. So we have VAB is equal to VC. There you go. And VA is equal to 20 volts. So we know VAB is equal to VA minus VB. So we get VB is equal to VA minus VC. Sorry. this should be 8. There you go. And finally, VA is 20 volts. So VB is equal to 20 minus VC. And this is your answer. Okay, so this is the answers from the example. So now let's move on to the concept of resistance. Resistance is the opposition to the flow of current. If there's resistance, it resists the flow of current, therefore resisting the flow of electrons. So it's governed by what we call Ohm's law, equal to or the equation is V is equal to IR. So current is the movement of electrons. Voltage pushes the electrons to move, and resistance limits the push exerted by the voltage. So look at this illustration right here. It's kind of like that. You have your ampere being pushed by the voltage, but being limited by the resistance. So to get a feel of how that works, let's look at what quote unquote a mechanical circuit. So some assumptions: the pipes are rigid and frictionless. Water does not lose velocity on the corners. The pump is rigid and will work for any value of water flow. So the pump just keeps accelerating the water that passes through it. Okay? So what happens? So the pump just accelerates the water. What will happen to the amount of water flow? So the amount of water flow actually just keeps on increasing and increasing and increasing and increasing. Does not lose velocity, right? Those are the assumptions. So that's what happens when you connect a voltage source to itself. It just keeps on pumping and pumping and pumping current until it creates an infinite amount or an infinite ampere current, and that's not possible, of course, in the real world. So what happens then if we have a bent pipe with some form of friction and velocity damping? Means as the water flow increases, the force increases here in this area. So what will happen to the water flow? So the water flow will keep on increasing in speed, but at some point, the force experienced by the water here in the bent pipe kind of forces it to have a constant flow. So it's kind of what we call a terminal velocity. If you remember the term, I think that's from Physics 71. So if the water flow keeps increasing, the force of friction right here, or velocity damping right here, also increases until it compensates for the force done by the pump. That's kind of like your resistance. So at steady state, it kind of compensates the voltage that is um, that is the output of the battery. So let's translate that now from your mechanical to your electrical circuit. So you have a battery connected to a resistance, which is any load. So your resistance converts your electrical energy into another form. For example, it could be light. So the flow of current is from your negative of the battery to the positive of the battery, and therefore going into the load, then going back to the battery, and there you go. This is your electrical circuit. So think of the flow of electric current as like the water flow from this example right here. So this is your electrical circuit now. Okay, now let's move on to the concept of electrical energy. So electrical energy is an energy form including related phenomena arising from the presence and movement of quantities of electricity. Let us break that down. Energy form. So it's transferred from a region within surplus of charges to a region with demand for charges. So that's the energy from let's go back from a excess of charges from this side, and this side demands charges. Therefore, you push that excess charge from here to here. So there you go. So you drive that those charges through electric potential energy. So related phenomena would be your lightning, static electricity, electromagnetism, electronics, communication, etc., etc. And from the presence, so the presence of charges would be your static charges, electric field, voltage, and movement. Those are your current, could be direct or alternating. So presence and movement of quantities of electricity. So energy conversion now is from your electrical energy can be transformed into other useful energy that, for example, mechanical energy for cooling, or heat energy and light for, well, for our dark nights. Or we can actually have other forms of energy converted to electrical energy to be transferred to our homes. So it could be your chemical energy, mechanical energy, or solar energy. So how do we quantify the power of your, or the power or energy that is transferred per unit time in our voltage sources? So power is the rate at which energy is being transferred. In terms of any device, the power is equal to its voltage multiplied by the current, and the unit is in watts or joules per second. So the current direction actually defines the voltage, the current direction and voltage polarity actually defines if the device is consuming power or generating power. So recall that the conventional current carries positive charges, and the tendency of positive charges is to move from a positive charge to a negative charge, or from a higher potential to a lower potential. So if that charge moves in, or if that current eh, moves from positive to a negative, the device exerts no effort because it's the natural flow of things. So recall that if your positive charge moves from positive to negative, it's just the natural flow of things. Therefore, it expends work, or it consumes electrical power. So the opposite is true when you generate power. So device B here moves positive charges from the negative side to the positive side. And it goes against the natural flow of things. Therefore, this device must be generating power. So take note of that. This is a useful useful tool to know if your device is supplying power or generating power, or if it's dissipating heat or consuming power. So for example, both cases you have 10 watts, but device A moves current from the positive to the negative. Therefore, it's consuming 10 watts or supplying negative 10 watts. In this case, device B expels current from the positive side, so it moves your charges from the negative to the positive side. The power is still 10 watts, but it's supplying 10 watts or consuming negative 10 watts of power. Okay, so to summarize, the movement of charges is current. So convention for current, flow of positive charges. At any node, the algebraic sum of currents is zero. Potential difference is voltage is the potential difference between two regions, and this is the difference in charge concentration results in the voltage, and the algebraic sum of voltages in a loop is zero. That's your Kirchhoff's voltage law. Electrical energy is work done to move charges through an element, And finally, energy per unit time is power. And depending on the path of the current, if it supplies power or if it consumes power. If you have any questions, you can discuss this in class. And I'll see you in class on Wednesday.